chi-square test. So it first identifies an acceptable deviation between the observed and expected values. Whereas in t-test, what we do in t-test, it actually says how the mean is actually varying between one particular sample and the same sample after some particular instant of time. So how that sample is actually varying in its distribution. With respect to the mean, it actually calculates. But here, each individual values is focused and how each individual values is actually deviating. That is the thing is focused in chi-square test. Like in student t-test here, having t-table, we also have here chi-square table, and we'll be using that. Hope you can see here. This is actually the chi-square table. The same degrees of freedom will be there, and the same significance values will be there. We'll be using these for calculating the chi-square values. Here, what we call is here also we'll be calling how I can accept a hypothesis and how I can reject a hypothesis. The same thing we are going to do here. Let us see how to start with chi-square test, right? So first, what we will do, we'll have some observed values, right? So the example what we are going to take is throwing a dice. Right? Can anyone say what will be the number of possibilities for when I throw a dice? Can anyone say what are the number of possibilities when I throw a die?
6, sir.
Six possibilities. Great. Six possibilities are there. And what is the expected value to get one? Expected means what is the probability of getting one?
1 by 6.
Great. 1 by 6. Right now, 1 by 6 of the total time, it should be like the same. So probability of getting 2 is also 1 by 6. Getting 6 is also 1 by 6. Now let us see some observed values for 1, 2, 3, 4, 5, and 6. Let us take a random value. Assume that 1 appeared 25 times, 2 appeared 29 times, 3 appeared 19 times, 4 appeared 33 times, 5 appeared 32 times, and 6 appeared uh, 27 times, right? So let us have this. Now using this, we can actually do a variation. So now what we have to calculate is, now like you rightly said, it is going to be 1 by 6, right? And each will be uniformly distributed, and each will be having a same value for that is every uh, die value should be equally same. That is, if it is 1, it should be same. For 2 also the number of frequency should be same. So everything should appear in the same level, right? So now this is actually the question that is given to us. Now whether these values are correct or not, we have to judge. That is, the judging is based on the expected values. And now I calculate the expected values. We know that the expected values when I throw a dice is actually 1 by 6 for each of the individual term, right? So now what I will do, I'll calculate the expected values based on that formula itself, right? One, two, three, four. I missed one thing. 4, 5. Need one more column. I'll insert it. 6. Yes. Now the frequency, the actual frequency should be equal to how much it will be there. Like you rightly said, it is going to be 1 by 6, but it is not 1 by 6 directly. The 1 by 6 of the total terms. Right now, I'll calculate the total frequency. Total frequency is equal to, I'll calculate as 25 plus 29 plus 19 plus 33 plus 32 plus 27. So what it is actually, we calculate that 25 plus 29 plus 19 plus 33 plus 32 plus 27. Right? If I'm right, it was actually 165. Right? So 165 is actually the total thing. If I was having 165, what is the probability of getting 1? How can I calculate this? Can I calculate this as 1 by 6, 1 by 6 into 165. Can I calculate it like this? Because it is actually, each thing should have a proper possible probability of 1 by 6. So 165 should be equally divided by each of the individual terms. 165 should be equally divided by each of the individual terms, right? So what I can actually do is to make the thing have a make without decimals. So if it actually increase our calculations, we can make it perfect divisible, like 6 to 12. Yes, if I make it something like if I make it 36, it make 168 and it becomes a perfect divisor for me, right? So the probability, the expected value to get the dice value as 1 is 1 by 6 into 168, right? Because the probability of getting 1 is 1 by 6 and the total number of samples is 168. So the number of samples what it will have is equal to 28. Am I right? It is 28, right? So 12, say it 840. Now what will be for 2? Can anyone say?
2 by 6 into 168.
2 by 6. How 2 by 6 will come? Everything will have equal probability, right?
Okay, sir.
Yes, everything will have an equal probability. This is the probability of the 1 to happen is 1 by 6. Probability of 2 to happen is 1 by 6. 3 to happen is 1 by 6 and so on. So the total probability will be 1 by 6 plus 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 1 by 6, which will be 6 by 6 equal to 1. That will be the total probability. So the expected value is a uniform probability. That is, everyone will have the same 28. This is actually the thing. So if you calculate all this also, you'll be getting 168. So this is the thing what I actually should be obtained. Now this is the expected value and this is the observed value, right? Actually, if I throw a dice and measure something, the expected value should be like this, but the observed value is this. Whether this observed value is obtained without any bias or any external circumstance or something, I need to check. So whether to accept it or reject it, that is the thing. The first thing, I need to set the hypothesis. That is, sometimes it may be biased also. I can bias a die and then throw. So now I set a hypothesis. So this is actually the step 1. That is, calculate total frequency and expected values. So this is actually the first step. Calculate the total frequency and expected values. Step 2 will be setting up the hypothesis. Now I will set my hypothesis so that I can say whether my hypothesis should be accepted or rejected. I say two hypotheses. That is, one is null hypothesis. And my null hypothesis states that dice is fair. This dice is thrown fairly. That is my null hypothesis. So my null hypothesis will be denoted by H naught. And I'll denote the alternate hypothesis also, which states that dice is unfair. Means it biased, right? Now we need to say whether this is actually which hypothesis should be accepted. If I accept the null hypothesis, then it means that alternate hypothesis is not accepted. So what is this? Is nothing but this is null hypothesis. Because H naught is actually denoted as null hypothesis, and H1 is alternate hypothesis. If one is rejected, it means that automatically the other is accepted, right? Now we need to say whether the null hypothesis is going to be accepted or rejected, right? That is what we are going to prove. So if it need to be accepted, then we need to prove that either using t-test or by using a chi-square test. We need to say that this is actually within the gray region and not in the red region. If it is in the red region, it means that they should not be accepted. So this is the case, right? Now we will go going into the thing. So far understood, right? So far no doubts is there. What we did so far is just the observed values is given. I calculated the total frequency, then I calculated the expected values. How I am calculating expected values? The calculation procedure may be different. In this case, in a dice scenario, the possibility for each value to occur is actually 1 by 6. And the total probability, what I actually have is here is the total number of sample is 168. So it will be 1 by 6 into 168, which will be 28 and so on. So each value will be having a uniform probability. Next, I set the hypothesis. Two hypotheses I have to set. Null hypothesis I'm setting, which I say that dice is fair. That is, there is no much deviation between observed and expected values. If I reject the null hypothesis, it means that the alternate hypothesis actually holds, which says that the dice is unfair, right? So far so good, right? So far, have you understood this?
Yes, sir.
Yes. Great. Now we go into the step 3, where the chi-square testing actually starts. I need to construct a table. Chi-square table I have to construct, right? Now in this chi-square test, what are the things I need to have is, I should take observed values, I should take expected values. Next, I need to find the difference between observed and expected values. This difference is called the deviation, and I need to take square of the deviation, whether because I need to calculate chi squared. Next, I need to divide or normalize it with the expected value. So I need 5 columns, I take those. So totally 6 is there, 1 2 3 4 5 6. So this is actually observed, and the observed can be denoted as O, and this is expected denoted as E, and this is O minus E, O, O minus E the whole squared. Next, O minus E the whole squared divided by E. O minus E the whole squared divided by E. Let me use the equations. O minus E the whole square divided by E. So this is actually the formula for chi-squared estimate. The chi-squared estimate formula is observed minus expected the whole square divided by the expected values. This is actually the formula for chi-squared, right? So using this formula, we are going to proceed. Let me write all my observed values. I have my observed values here. That is 25, 29, 19, 33, 32, 27. These are my observed values. I take those. So what is the first one? 25. Can anyone help me? What are the next values? Anyone see this? And when I go down, please explain me. 25. Next. What is next? 29. Next.
19.
19. Okay, I need to go up again.
33.
33. Okay. 33.
30, 32,
30, 32.
27.
Oh, 27. And expected values. I need to calculate the expected value. I already calculated. I have this all 28. So expected values is all 28. 28. 28.
Sir,
Yes, Pa.
you took 33 as 36 now, sir.
Oh, yes. Thank you. Thank you. I just modified here to round it off. Right. So the calculation can be easy. So I should change here also. Thanks. This is the right 33 to 36. Now calculating the difference O minus E. 25 minus 28, that is minus 3. 1. This is minus 9. This is 12. And this is 4. And this is again minus 1. What is this? 9. 1. 9 into 9, 81. 144. 16. And again 1. Right? We have this already. Now finally coming into this 1 minus E the whole square divided by the expected values, right? We need calculator for this. 9 divided by 28. So I get here 0.3214.
36 minus 28, you took 12, sir. It's 8.
Oh, sorry. 8. Before. Any other mistake is there? Yes. Hope others are correct, right? Others are fine?
Yes, sir.
Yes, great. Now 1 divided by 28, I need 1 divided by 28, 0.0357, 0.0357, and 81 divided by 28, 0.8928, 64 divided by 28, 2.2857. Next, 16 divided by 28, 0.5714, 0.5714, and 1 divided by 28 already we have 0.0357, right? All the calculations are going good, right? Yes. Can anyone see that? Whether the calculations are going good, right?
Yes, sir.
Yes. Great. Now we actually found these values. Now I need to take the summation of O minus E the whole square divided by the expected values. Now we took all the values ready. Now we just need to take the summation value. So the summation value, let me write the table somewhat above. So these values I need to take the sum. That is, I take my calculator again. 0.3214 plus 0.0357 plus 0.3214 plus 0.0357 plus 2.8928 plus 2.2857 plus 0.5714 plus 0.0357, right? So it is giving me 6.1427, right? Hope it is correct, right? 6.1427. 6.1427. So this actually is the chi-square critical value. This is actually meant as the chi-square critical value. Now this criticality will increase when it is actually in the red region, and the criticality will be accepted if it is in the gray region. Now we need to find in which region it actually falls. This is the thing we need to find, right? Now the step 3 is okay, right? Now we will go into the step 4, that is going into the chi-square table and then finding the particular value, right? Now, can anyone quickly say what will be the degrees of freedom here?
5, sir.
Great. How?
6 minus 1, sir.
N
Great.
minus
6 minus 1.
160.
6 minus 1, 5. Very good. And we need to take the significance level. Here in the problem, we didn't have the confidence level given. If confidence level is given as 95%, we can take like 1 minus 95 divided by 2, like that we can take. But the confidence level is not given. So the alpha value, we have to take the alpha value by lambda. By randomly, we can take the best values of alpha. We can note that the best value of alpha can be between 0.01 to 0.05. Any values between that we can take and we can use that for estimation, right? Now we can use 0.01 as a significance level. Now both the thing. So I'll also write, since I'm going to share this, a small note I write here. If the significance level is not given in question, you take it between the suitable values for significance level. Alpha is equal to 0.01, okay, to 0.05. So between these ranges, if you take, it will be great. Now we took 0.01. I go to the chi-square table, right? Now you can say me, where is 0.01? Here it is, my 0.01 is present. And as you said, my degrees of freedom is going to be 5. So in this range, I need to search, right? In this, what will be the value for me? my 0.01 range, and in the degrees of freedom 5, what is my value? 15.09, right? From chi-squared table, the estimated value, sorry, the chi distribution value is 15.09, right? This is actually the curve which we have. Now let me go into the paint window and draw a small thing. So this is the distribution we actually have, and in this distribution, right? Now the value which is actually going to be in my accepted range, sorry, the accepted gray value range is going to start from 15.09. So assume that 15.09 is going to be somewhere here. This is going to be 15.09. Beyond this particular range, I will not accept anything. So everything after this will be in the red region. I make it red. I make it red. Right, now you say, now what is the value we obtained is the critical value for chi-squared is 6.1427. So where 6.1427 lies, whether in the in this side or in the left hand side it will lie. In this sorry, in the right hand side or in the left hand side it will lie. Whether it will lie in the white region or whether it will lie in the red region. 15.09 is actually the separator. In this range, we actually have the red region, and in this range, we have the Y region. And the significance level, what we have here is alpha is equal to 0.01. Okay, very good significance level. That is 99% confidence we have here in saying this particular result. So here, now you say whether it will lie in the white region, that is 6.1427, will lie in the white region or will lie in the red region.
White, sir.
White. So shall I accept or shall I reject? If it is in the red region, I can actually reject. But we know that it is to be actually somewhat around here, right? So my range will be actually, I will draw something like here, where 6 may be present. This is actually 6.14. Right? This is actually 6.1427. So I can accept this hypothesis. This hypothesis can be accepted. So there is not much deviation between the observed and expected values. So I can accept this particular hypothesis. So what is accepted? H naught is accepted. So I can write here. So result, I should write here the result. Actually, the symbol for chi-squared is actually this. Chi-squared will be written like a thing like this, and then this is what chi-squared. Let me find this symbol here. If not, we can actually, you actually see in the paint window, that is actually the symbol for chi-squared. Really it will be present here, but we have to search where it is actually. Right, I don't want to make waste time in searching it. But this is actually chi-squared. Right, the symbol for chi-squared is just put a cross, and then this is actually chi-squared. Chi-squared test. Right, now we go here. The chi-squared value lies in white region, that is 6.1427 is actually less than 15.09. Hence, what we say? We say that H naught, that is a null hypothesis. H naught, the null. What H naught says, dice is fair, is accepted. If H0 is accepted, automatically I say H1 is actually rejected, right? So if H0 is accepted, automatically I can say H1 is rejected. There is no don't want separate proof for this. Both are either null hypothesis should be true or alternate hypothesis should be true. If null is actually true, then alternate is actually false by default, right? Now, can you understand how to do chi-square testing? Yes, is it easy?
Once again, explain, sir.
Once again, I'll explain. Okay, right? So now I have an observed and expected values. Anyway, I'll give you a separate table for the difference between t-testing and chi-square testing. The general difference between t-testing and chi-square testing is t-testing will find the deviation between two distribution after applying some treatment over the first distribution. How it will find the deviation is with respect to the mean. We will be calculating something called as error bound around the mean. How much error is there around the means, because mean can explain the distribution completely. That is actually t-testing. Here it is not with respect to mean or anything. Each individual variable will be taken into consideration, and what is the deviation between the observed set of values and expected value is actually calculated. So the deviation between observed and expected value is 1 by 6 into total samples. See, I'm repeating again. For this problem, it is 1 by 6 into 168. What is the usual procedure? It calculate all the total frequency and find what is the probability or the expected value for this particular value to exist. For like you said, when I throw a dice, the probability of getting a dice value as 1 is 1 by 6. So 1 by 6 out of 168. I need to take 1 by 6 into 168 I take. So all of them will have an uniform distribution. So this is the case, right? Have you understood up to step 1? Yes. Shall I move to step 2?
Yes, sir.
Yes. In step 2, what I said, now it is actually my own thing where I test a hypothesis, I check that whether the dice is fair or dice is unfair. Usually the hypothesis can be given in question or you can set. Mostly it will be given in question. So you need to prove whether the hypothesis is true or not. The hypothesis in the H0 says that dice is going to be fair, means that you need to accept the hypothesis. Accept in the sense the deviation between observed and expected values is not greater than the critical value, right? That is actually accepting. And H1 is the alternate hypothesis, which says that dice is unfair. Right? Next, now comes a chi-square table. The formula for chi-square is observed minus expected the whole squared divided by expected, right? So this is, I think, that is sum of observed minus expected the whole square divided by expected. So I list all the observed values. So where I take this observed values, these are my observed values, I take all these, and these are my expected values, I take all these. I calculate the difference between observed and expected. I square the difference. Then I use the formula, the summation observed minus expected the whole square divided by expected. Right? When I add all this, I'm getting a value as 6.1427. Right? That is with respect to each individual value I'm taking. Right? Now, whether the 6.1427 deviation can be in accepted or not accepted, yeah, I have to calculate. Now I go for the degrees of freedom. I say degrees of freedom is going to be n minus 1. N is actually 6 because I having 6 different values. So I say 6 minus 1 as pi. And the significance level alpha is going to be 0.01. Alpha value is actually not given in my problem. So the suitable values for significance level alpha is actually between 0.01 to 0.05. That is from 95 percentage to 99 percentage you can actually use for any problem. So it is up to you. If it is not given, we take the value between 0.01 to 0.05. We take the very closer value, the most highest level significance value, that is 0.01. Next, I go into the chi-square distribution value. How to find this is, I have the degrees of freedom ready. I have the significance level. I go to the chi-square table. In chi-square table, 0.01 is actually here, and the degrees of freedom 5 is here. So the intersecting point of this degrees of freedom and the chi-square testing is actually 15.09. I take this and I put here. So I go into my distribution here. In the entire distribution, all the points in the white region is actually accepted. and all the points in the red region is actually rejected. So what I do, this accepted range of values, I need to check whether my critical value calculated with as the deviation between observed and expected is in the white region or red region. I need to calculate. I found that it is actually present in the white region. Right? I'll paste it here. Yes. If you see here, the accepted value is actually present in the white region. How the 6.14 came? This is actually the summation value, 6.1427 it took. So it is actually in the white region where others are in the red region, right? So since it is in white region, I can accept the given hypothesis. So H0 is accepted. So automatically I can say that H1 is rejected, right? So let us go into another problem. The only difference what you can see with respect to the next problem is this particular case. How to calculate the expected values. Others are actually exactly same. How to calculate expected values is actually the thing we have to check here. Example 2, right? We can have this example. Now I'll check the observed values first. I'll take that. It's from one of the books. So I'll take that and I'll say the question. Yes. So now the thing is, we need to check the qualification of a person based on his marital status, right? Let me take qualification. Let me draw that table first. It's 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Right. So qualification slash marital status. So this is actually in one case. And here I mentioned several qualifications of a person: middle school, high school, next bachelor's degree, master degree, PhD. But others can be some other degrees like diploma or something, right? Now, if a person is never married, what will be his what degree he will have? If he is married, how much degree he have? If he is divorced, what will be his degree? If he is a widowed person, what will be his degree? So this is actually the thing we have, right? And to reduce the question thing, we can remove the others because it will increase our space. So this is actually the thing, right? For this question, we are going to use the chi-squared estimation, right? Now it looks somewhat good. Now let us give some values here. Say, suppose here 18 members who are never married have done up to middle school, and number of people done up to high school is 36. Number of people bachelors is 21, 9 and 6. We have like this. And married, 12 people in middle school, 36 in high school, 45 in bachelor, and 21 in 36 36 in master, 21 in PhD. Similarly, for divorced, it is going to be 3, 9, 9, 6, 3. And it is going to be 3, it is 6. 9, 9, 6, 3. So this is actually the question given to us. Now for this question, we need to see how the values are going to be there. That hypothesis to be tested is, now the marital status is given and the qualification is given. The problem says that a person who are never married, it will be 18 people who never married have completed only up to middle school. 36 people who have never married have completed up to high school, and only 6 people who are never married have completed PhD. So this is the case given here. Like this, many values are given. Now, what is our role is we need to set two hypotheses. Hypothesis number one is marital status has no effect on this particular type of degrees. Right? Studies and marital status is no longer related. There is no relation between them. Other hypothesis alternate will be there is a relation between marital status and this particular studies. So that is actually the two things what we are going to say. Now, what is the first step is calculating the total frequency, right? Now, the question is understood, right? The thing is, I'm having different kind of marital status and different kind of degrees, and the number of people who are actually studying each particular degree in their marital status is given, right? I call statistics is taken, right? The question is clear. Now we need to take the total frequency of this 18 plus 12. It is going to be 30, 36, 39, and this is 72 plus 8, 18, 90, and this is 18, 19, 29, 39, 79, and 84. If I make any mistake, please inform me. 12, 21, 51, 57, 9, 15, 16, 36. Am I right? The calculations are okay, right? This is the total. And what is over here is 9 plus 6, 15, 46, 56, 64, 70, and 100, I hope. Am I correct? This 100? Shall I use calculator? 15, 16, 26, 36, 72, 8. I think 90 is coming. Is it 90 or 100? Now coming to here, what is the total here? 12 plus 36 is going to be 48, 88, 93, 123, 129, 130, and 150.
150.
Okay. And 18 plus 30, 33. Next step is actually 9, 18, 21,
30.
7, 30. And what is the total of all? This is actually the total of everything.
303, sir.
303. On both ends, if you calculate also, you get 303, right?
Yes, sir. Same.
Yes.
303 ఉంది.
Yes. So now we go into the thing. Now the frequencies are ready. Now with this frequency, we need to calculate the observed values, right? Sorry, expected values. Going to the expected values, I take the same row again. So expected values is nothing but the values which is actually possible with the probability, with some probability. How to calculate each of those individual values is to just delete everything. Now the calculation is something slightly different, right? Now what is the possibility of getting a particular variable to get satisfied here? That is, this is actually never married to middle school is actually just 18. Never married to this is actually 18. How this 18 actually comes? This 16 is actually the proportion of 39 and 90, right? This is actually the proportion of 39 and 90, right? So now how to calculate this expected value over here? Just to actually multiply these and these and divide it by 303, that is will be the expected value for this, because this is actually obtained from 39 and 90, that is actually 18. So divide it by 303 and that will be the probability for getting this. The probability for this is this into this divided by the total sample size, right? So what I do, just I take, it is in a matrix form, you just take like this, that is 39 into 90 whole divided by 303. So this is actually will be the value, and the value of this will be 39 into 90, 39 into 90, 3510 divided by 30. So it is actually 11.58. This is actually the expected value. That is 11.58. I write here. This 11.5. Similarly, how to calculate this? Can anyone say how to calculate this?
90 into 90 by 303.
Great, great. 90 into 90 divided by 303. If I calculate this, 90 into 90 divided by 303, and I get 26.73. I get 26.73. I go here. It is 26.7. Similarly, this 84 into 90 divided by 303. 84 into 90 divided by 303 is 72. It right? No more much deviation is there. 84 into 90, 7560 divided by 303. It is 24.9. 24.95. Next, 57 into 90. 57 into 90, 5130 divided by 303. That is 16.93. 16.93. Finally, PSD, only one value is remaining. That is 33 into 90, 2970. 33 into 90.
9.801.
9.801. 9.801. Right. So you need to calculate all these four. So how to calculate this? 39 into 150 divided by 303. That should be calculated here. So we need to do for all, right? Actually, I have, by the time I do this, anyone do for divorced and widowed, so that we can complete it soon. I do it for the married now. Yes. So this married will be 39 into 150. 39 into 150 is 5850 divided by 303. That is 19.30. And high school. 90 into 150. 13,500 divided by 303. I'll get 44.55. And 84 into 150. 12,600 divided by 303. I get 4158. And 57 into 150. 8550 divided by 303. 28.21. Next, 33 into 150. 4950. I get 16.33. I have completed this. Can anyone say what will be the divorced here? Have anyone calculated the divorced? Anyone?
39. 4.24.
4.24. Next,
90 into 33 divided by 9.801.
9.801. Next, I just use the calculator again. 84 into 33, 2772 divided by 303, which is 9.14. And yes, at least calculate for the next one final thing, that is widowed. Okay, I'll calculate complete for this. 57 into 33, 1881 divided by 303, that is 6.207. 0.207. And finally, we need only 2. Next, 3.
3.594.
3.79. Okay, 3.79.
3.594, sir.
Okay, 3.59.
Yes, sir.
Read out. 39 into 13. 1170 divided by 3.86. Next, 90 divided by into 3. 90 into 30. 2700 divided by 303. 8.9. This is 84 into 30.
8.316.
8.316. And this is
5.64.
5.64. Finally,
3.26.
3.6.